You are here for the last talk of the day, using undocumented CPU behavior to see into kernel mode and break KASLR in the process. Put on by Anders Fogh and Daniel Gruss. Daniel, take it away.
Okay, thank you. This talk is about using undocumented CPU behavior to see into kernel mode and break KASLR in the process. About a year ago, I was preparing a talk for Black Hat 2015 about detecting rowhammer, when Daniel and his team came up with the way to do rowhammer in JavaScript. That marked the first time that Daniel's and my research collided. It has collided a lot the last year, and finally we decided that it might be a good idea to cooperate instead of competing. And what you're about to see here is the first result of our cooperation, and I hope you like it. So before we actually start with the presentation, just a couple of things to set straight. This talk is about a class of microarchitectural attacks. It's not about software bugs. It is, however, about how CPU design can be used as an attack vector. And with microarchitectural attack, we mean it's not about the instruction set architecture, which is what Intel promises to software developers that it will keep. It's about how the instruction set architecture is implemented. That is the level below that. We will be focusing on Intel x86 64. Lots of the stuff that we'll be doing applies to other architectures as well. What we want you to take away from this talk is, on a macro level, that CPU design is security relevant. And on the micro level, we'll want to make clear that the prefetch instruction leaks important information, and that we can use this information to locate a driver in kernel mode, that is, defeat KASLR, and we can translate virtual addresses to physical addresses, and we can use this for other attacks. So this is a short overview of the organization of this talk. I will not read this slide out aloud, so spare you that. Turning to the introduction, we found something in an Intel manual that read something like this. Using the prefetch instruction is recommended only if data does not fit in the cache. Use of software prefetch should be limited to memory addresses that are managed or owned within the application context. Prefetching the address that are not mapped to physical pages can experience non-deterministic performance penalty. For example, specifying a null pointer as an address for a prefetch can cause long delays. What somebody like Daniel reads when he sees this is, please only use the prefetch as Intel intends, or else Intel will be angry, and there's no reason why anybody would measure the execution time. So, short, who am I? My name is Anders Fogh. I'm a principal security researcher for GData Advanced Analytics. I've been playing with malware since 1992, and you can reach me on Twitter or by email.
Hello from my side. My name is Daniel Gruss, and I'm a PhD student from Graz University of Technology, where we have also worked on this project. Later on, recently, I joined Microsoft to do an internship in Cambridge, UK. You can also reach me on Twitter or via email. So this was a joint work with some other researchers from TU Graz, Clementine Maurice, Moritz Lipp, and Stefan Mangert, who are unfortunately not here, but it was a group collaboration and team effort. Okay, let's start right away with some background on the memory subsystem. So for the first part, we want to talk about CPU caches, how CPU caches work. You have relatively fast CPU nowadays in your computer, but the DRAM is still very slow, because that's how DRAM works. And there is some idea to make the accesses to your memory faster, because you need a lot of memory, but only need a small fraction of the memory in a high frequency. The idea is to buffer the frequently used memory in the CPU in some smaller but faster memory locations. Every memory reference that any program in your system does goes through the cache usually, and it will be fast because it's buffered in the cache. The cache is entirely transparent to the operating system and programs, so you won't notice that the address is actually cached, except for one artifact, and that is the access latency. So if you measure the execution time of a memory operation, then you will see that the access latency for a cache hit is much smaller than for a cache miss. And here you see that for this particular CPU, the cache hits were around 70 cycles, whereas the cache misses were around 220 cycles most of the time. If we look at the structure of caches in modern CPUs in detail, today you have CPUs with multiple cores, and each of those cores has private caches, the level 1 and the level 2 caches, and they all together have one big shared cache, the last level cache, the level 3 cache, which is up to several megabytes. And the small caches, the level 1 cache, for instance, it is only like 32 kilobytes of data cache and 32 kilobytes of instruction cache. And there is a reason for that, and this is that you want to work with virtual addresses here. The level 2 cache is larger, and also the last level cache is larger. There you have to work with physical indexes to find the right location in the cache and the right cache set to store the data that you want to load from DRAM. There is a fixed mapping from physical addresses to locations in the cache. And this mapping, this is fixed in the CPU. So if you have one memory location, it will always go to the same memory location in the cache. There are two operations basically to manipulate the cache utilization, to optimize the cache usage. That is first the prefetch instruction. It is sort of a hint to the CPU where you can tell the CPU, please load this into the cache. I think I might need this in the near future. And there is the CLFlush instruction, which basically does the counterpart. It tells the CPU, I don't need this part, throw it out of the cache. Or rather, for coherency reasons, you can also use the CLFlush instruction to tell the CPU, I'm not sure this value in the CPU is still up to date. Please flush it to the memory and then reload it from the memory on the next access. Both instructions are based on virtual addresses, so they need to perform somehow this translation from virtual addresses to physical addresses because the last level cache is physically indexed. You can remember that for later because we might need that later on. When we talk about prefetch instructions, actually there are 5 prefetch instructions. First we have the prefetch T0 to T2, which give different sort of hints where the data should be loaded. And as a rule for the thumb, you can say that the T2 instruction will fetch it rather to the level 3 cache, whereas the T0 instruction will rather fetch it to a cache that is closer to the execution core. The prefetch NTA instruction allows you to tell the CPU, okay, I will probably only access this data once, you can throw it away afterwards, but please load it into the cache right now. And then there is a prefetch W instruction which tells the CPU, yeah, I'm intending to write to this variable, maybe, but I'm not, could you please load it into the cache, into my local cache, and maybe invalidate it for the other caches so that I can really write to it without any delay. The actual behavior of the prefetch instruction varies widely between the different CPU models, so whether T0 fetches to L3 and L1 or L3 and L2 and L1. So you cannot really rely on a specific behavior, but we found out that this is also not necessary because we are just interested in some corner cases. The prefetch instructions, they are somewhat usual, not only that they have to translate virtual to physical addresses, they are unusual in 2 ways. The first, I already said, they are hints, so the CPU can ignore them, but most of the time the CPU will not ignore them. The second unusual property is that it is probably one of the few instructions in the Intel manual where it says this instruction does not perform any privilege checks and it does not cause any exceptions. And if you read anything in the Intel manual and it says it does not cause any exceptions, then this sounds a bit dangerous. So why do we actually have this address translation with the virtual and physical addresses? If we look back 20 or 30 years, or if we look at small embedded platforms, we actually don't have virtual addresses. We only have physical addresses. And you can only run like one program, one system on this chip. And you don't have any isolation between different threads on this CPU. With the Intel 386 CPU, virtual addresses have been introduced, and they allow to isolate different processes on the same CPU by providing different address spaces to them. So there is a map inside your hardware, and you can configure this map, and you can map from virtual addresses, like the pointers that you usually have in your programs, to real physical addresses on the hardware. Every application has its own virtual address space because it has its own map from virtual to physical memory. In this map, you not only have the translation from virtual memory to physical memory, but you also have the privilege settings for this memory region. And the privileges are then checked when you access a memory address in this memory range. The privileges are then managed by the operating system kernel, so you can do this dynamically, and the operating system can manage what you may and may not access. For instance, you should not be able to access the kernel. The address translation on x86 looks like this. So we have a 4-stage translation. It looks more complicated than it actually is because it does the same on all of the 4 levels. So you start on the top left corner with the CR3 register, which is a CPU register, and it gives you the physical base address of your translation tables. And it's in this case the PML4, the page map level 4. And this page map level 4 has 512 entries. Every of those tables here has 512 entries, and each entry is 8 bytes in size to store a 64-bit pointer, basically. And therefore, each of those tables is 4 kilobytes in size, which is, again, pretty nice because you have 4 kilobyte pages on Intel CPUs, and then it's easy to organize all the memory with a bitmap. The virtual address. So we have a 48-bit virtual address here, and so yeah, we know we have 64-bit address space, but right now we can only use 48 bits. And it's divided into different parts. So we have the first part is the page map level 4 index, and this index has 9 bits, and it chooses the right page map level 4 entry from this first table. Then exactly the same happens on the next level, the page directory pointer table. Each of those page directory pointer table entries organizes 1 gigabyte of your virtual memory. And here you have the option to directly map a 1 gigabyte page to physical memory, or you can map a page directory. And this page directory will divide the 1 gigabyte page into smaller blocks. The page directory then again has 512 entries, so you have 2 megabyte pages that you can map in the page directory. And on the last level, the page table, you again have 512 entries, and then it divides the 2 megabyte page into 4 kilobyte pages. Now, these tables are quite large. They are multiple kilobytes, each of them at least 4 kilobytes, and you have multiple tables per layer, so you will probably have 1 PML4 and multiple PDPTs and multiple page directories. So this adds up, and you have several kilobytes of physical memory that is actually used to translate virtual addresses to physical addresses. So this is kind of weird. To access physical memory, you need to access physical memory to translate your virtual addresses to physical addresses. This is kind of weird, and this would also be very slow, and therefore Intel had the idea to introduce caches for this part as well. So here we again have a cache hierarchy similar to the level 1, level 2, level 3 caches, and it starts with the instruction TLB and the data TLB on the top, and then we go next to the page directory entry cache, the page directory pointer entry cache, and then the PML4E cache. The CPU starts the lookup on the top, so it first checks whether there is an entry in the TLB, and if it is, it can already abort and get the data from the cache. or from the DRAM. If there is no such entry, it probably has to go further down on the lookup hierarchy, and if it doesn't find any entry in any cache, then it has to look up the page table structures in the system memory, in the DRAM.
So before we can proceed with an attack, we need to know about how modern operating system uses this paging system. And the first thing we need to talk about is that the kernel is mapped in each and every process on the system. This is by necessity. It turns out that user applications often use kernel services like reading from a hard disk, stuff like that. And for that, it calls into the kernel where a privilege escalation is being made, and then the stack is being changed. So this means that the kernel is present in every user mode application. However, it typically protects itself from access using the page tables. For this talk, we also need to talk about address space layout randomization. In this case, it means that the kernel and the drivers are loaded at random offsets in virtual memory. And the idea behind this is that it mitigates code reuse attacks such as return objective programming. There are other code reuse attacks that are mitigated with this method as well. It also mitigates attack based on read primitives or write primitives. That is the classical exploits. And the idea here is that if an attacker does not know where in memory the code or the data that he needs to use is, then he is unable to mount an attack. What, however, can happen is that if a kernel or a driver address is being leaked, it defeats the mitigation. The final thing that we need to talk about is the kernel direct physical map. It's not present on all operating systems, but it's on many operating systems. And the kernel physical map is, direct physical map is, means that the entire physical memory is mapped into the kernel space. And the reason is probably convenience, because this allows the kernel to change any memory at any time for any reason. This is without changing the page tables or doing stuff like that. So it's convenient and it speeds things up. It is not on all operating systems. It's available on OS X, it's available on Linux, it's available on BSD, and quite interesting, it's available on Zen PVM, that means Amazon EC2. It's not available on Windows. We should take note of this because one of our attacks actually uses this kernel direct physical map. So that moves us on to actually talking about the side channel that we're using for our attack, the prefetch side channel. And before we go ahead, we just summarize what we had thus far. First, the kernel is mapped into every process. 2, the prefetch instruction takes a virtual address as input. To manipulate the L3, a physical address is needed. The prefetch instruction must translate. 3, the prefetch instruction does not track privileges, meaning any address can be prefetched. And 4, translation is cached. And lookup searches caches in a fixed order. This leads to the question, caches are supposed to speed things up. Can we figure out the order where the lookup succeeds or fails by a timing attack? And we can actually measure a difference. And when we do that, it looks like this. And if you remember the cache lookup hierarchy graph, you will find that this is an almost exactly match of what you would expect when measuring latency on the prefetch instructions. That the fastest is if it's in the TLB, and the slowest if it has to go to physical memory. It's worth noting here that that is exactly the reversed order of the page table lookup itself. And that has a purpose for Intel, because most operating system tends to use small pages, not much use for gigabyte pages in real-world applications. So the idea here is, would this also work for inaccessible kernel memory? And you already know the answer, because the prefetch instruction doesn't track privileges. So let's turn to what we can do with the kernel with the prefetch instruction. Before we actually do an attack, we need to define an attack primitive. And we call this our translation oracle. And it works by timing the prefetch instruction on an arbitrary address, and it will recover the translation level. How this works is we time the prefetch instruction. The time that we get out of that, we match to the diagram you saw on the last frame. It's fairly simple. You start at the y-axis, you end up at the x-axis, and you'll see where you get. We can use this to recover a map of the kernel. And what do I mean by map of the kernel? Most of you probably know the proc-pid page map in Linux, which is nowadays privileged to access because it's useful for attacks. Remember, our attack is a CPU-based attack. It's not about an operating system. This means that we can recover this map for Windows as well. We can recover it for other operating systems. It's just that we can recover it from basically most any operating system from unprivileged code execution because the prefetch instruction is unprivileged. So we start out with a breadth with searched. And that is we search the memory for PML4 entries, and we do this by searching in half terabyte steps. Remember, this is half a terabyte cache. And if we find one, we know that we can, whenever we find one, we know we can skip the next half gigabyte. And we do this for each of the 4 translation levels, and we end up with a complete map of the kernel. And to complete this process, it takes anywhere from seconds to hours, depending on how many pages are actually mapped by the operating system and what kind of pages there are. Typically, what you'll have is a lot of 4K pages. The amount of time you need increases with stuff like shared memory. If you memory map the same file a million times, you'll have a lot of page entries, and it'll take a long time. However, at this point, we should probably note that an attacker rarely needs a map of the entire kernel. He is usually satisfied with a very small subset of the kernel. So typically, he is able to run this attack in seconds or less. We will actually see this in one of our case studies later. So that leads us to the next attack primitive that we have. And we call this the address translation oracle. The address translation oracle is there to determine whether a virtual address, P, and another virtual address, P bar, map to the same physical address. And the way this works is that we first flush P from the cache. The CL flush instruction actually does cause access violation. This means that this has to be a user mode address where we have access. The second step is we use the prefetch instruction to load P bar into the cache. And we remember the prefetch instruction doesn't check privileges, meaning that P bar can be a kernel mode address. And then we time the access of accessing P. And if accessing P is fast, we know that P maps to the same physical memory as P bar. One should be aware here, prefetched instruction is a hint. That means that the reverse is not true. If it was slow, it does not mean that they do not map to the same physical memory as P bar. So just be aware of that this can occur. Yeah.
Okay. When we speak about measuring the execution time of instructions, we actually have to know how the Intel CPUs, modern Intel CPUs execute instructions, and they don't necessarily do that in order. They reorder instructions to optimize the execution flow. And if we look at a simple example with 3 different instructions and we want to measure the middle instructions with RDTSCP, then the CPU is actually allowed to reorder the instructions like this. So instruction 2 may be executed before the RDTSCP, and instruction 3 may also be reordered to be executed in between or even before. And this is really bad because then we don't know what we actually measured. We measured something, but probably not what we wanted. Fortunately, the RDTSCP instruction provides us with a different property. So if we look at reordering in the opposite direction, in the forward direction, then we see that instruction 1 may not be reordered so that it is between the 2 RDTSCPs, and also instruction 2 may not be reordered so that it's outside of the two RDTSCPs. The same properties hold for mfence. Mfence is used to serialize memory accesses, and here the same properties hold, so the instructions may not be, the memory referencing instructions may not be reordered in the forward direction, but they may be reordered in the backward direction. So this is not allowed. So we need some additional instruction that provides full serialization of our instruction sequence. And actually there is an instruction that allows us to do that, and that is CPU ID. So we have to run CPU ID before and after the instruction that we want to measure with a high cycle accuracy. Now CPU ID is an instruction with a huge overhead, and we observed noise while we measured different instructions when using CPU ID, so we had to figure a way to make the measurements really reliable. If we look at the prefetch instruction, the prefetch instruction is not ordered with respect to RDTSCP, so this is allowed, and this is also allowed. So when we want to measure prefetch, RDTSCP is not a help at all. And the same goes for mfence. So again, it may be reordered in any direction, and we cannot just rely on RDTSCP and mfence. So if we want to measure the execution time of a prefetch instruction, we actually have to come up with a sequence, and we came up with the following sequence. We start with an mfence to serialize memory accesses, then RDTSCP, then CPU ID, then the target instruction, and then the same instructions in the opposite order. And this allows us that the prefetch instruction in the middle may actually be measured to a high cycle accuracy. The CPU ID instruction might introduce noise, we have observed that, but the noise should cancel out over several measurements. If we want to reduce the noise from CPU ID instead, and if we don't measure a prefetch instruction, then we can instead execute the following sequence, so mfence, then CPU ID, and then RDTSCP, and this will provide us with a better accuracy, so we don't have to perform that many measurements for this kind of measurement. When we measure the execution time of the prefetch instruction, we use prefetch NTA or prefetch T2 because they target the last level cache mainly, and for the memory accesses we just use a move instruction as is used for most memory accesses. Yeah, next we talk about the feating Windows 7 KASLR.
So here is a case study in how we can actually mount an attack with what we got so far. And first we need to notice that Windows 7 memory layout is pretty fixed. We know that the HAL and the kernel is always located between the addresses where it says start and end, and for kernel drivers is located in another region. Where they actually start is randomized, but they are in these regions. This means that when we want to launch a recovery attack, we only need to do a fraction of the kernel, which means that we can actually mount this in less than a second. And this is actually how we start to break KASLR on Windows 7. We map the driver's address space and use translation recovery attack. Remember, we haven't broken Windows 7 KASLR until we know where a driver is in the memory, because otherwise we would not know where there is something that an attacker could use. The second step is we evict the page translation caches, and there are two different ways that we can do this. We can use a sleep API in Windows, which causes the current process to be swapped out and another process swapped in, and when we get swapped back in by the scheduler, typically we'll see that the translation caching has been cleared, and we can use that. Another and faster way that we can do this is we can access a lot of memory in a large, otherwise irrelevant buffer, and since we're accessing a lot of memory, it will be optimal for the CPU to have these addresses in the translation caches, and this means that all the kernel modules and drivers will be removed from these caches. The third step we need to perform a syscall to the targeted driver. what we're hoping to accomplish with that is that we hope the addresses that is used by this targeted driver will be placed in the translation caches, in the paste translation caches, and that we can measure it afterwards, and that is, in fact, step 4. In step 4, we take an address from the list we found in the first step, from the page translation, that is where memory is actually mapped, and we time the prefetch for that. And we do that for all pages that we found in the first step, and the fastest average access time is then the right address. There's a bit of noise in here, so we actually repeat these 5 steps 100 times to get an average. And when we look at that graphically, it looks something like this. And you'll notice here that the red bar is the address that we were looking for in a driver, and the very small blue dot below signifies that this is the smallest average here. And in this way, we can locate a driver in virtual memory for an unprivileged access using just the prefetch instruction.
Okay. Then we will discuss how we exploit direct physical maps. And therefore, we will just go one step back first. So why is a direct physical map a problem? Let's think of kernels like 10 or 20 years ago. Assume that you have like a write for primitive, and you can overwrite an address in the kernel. You could, for instance, overwrite some return address, and then the kernel would execute user code. If you write a user code pointer there, you are still running in with privilege mode in ring 0. So if you just overwrite the return address with the user space code address, then you would actually run the user code. If this is for some reason not possible, you could still try to overwrite the stack pointer and then switch to a user space stack, and then do some return-oriented programming by providing a nice prepared stack in the user space. Now, this is not possible on modern CPUs anymore because there are countermeasures against that. The first is called supervisor mode execution prevention. So we cannot jump to user space code anymore because the hardware prevents that. The operating system configures that, and then the hardware prevents us from jumping there. And the same goes for switching to a user space stack. So we cannot simply do that because supervisor mode access prevention prevents us from doing that. Now, in 2014, there has been an attack showing that the identity mapping, the direct physical map in the kernel, can be exploited to do the same, to launch the same attack. Because every address that is valid in our user space program will also be in some accessible region in the kernel memory in this direct physical map. So instead of just jumping to the user space, we just take the physical address at the base offset of the direct physical map and jump there. And this is known as return to direct attacks, and this was presented by Kernel et al. At Black Hat and Usenix in 2014. So what is the solution against those attacks? So they suggested one solution that involved getting rid of parts of the direct physical map, like the parts that are mapped in the user space binary. But actually, Windows doesn't have a direct physical map, so why don't we just get rid of the direct physical map in OS X and Linux and other operating systems as well? That might be a solution, right? Apparently not. It's too complicated. Instead, we decided we do not leak physical addresses to the user. So you cannot access the physical address map anymore, and this is the solution. Perfect, problem solved. So what we can do now is we can circumvent this mitigation, because it's not really a good mitigation, and we can determine physical addresses or direct physical map addresses using prefetch. So we use our translation recovery attack to find the direct physical map if we don't know where it is, if the base offset would be randomized. Usually it is not, so we can skip this step and just do the second step right away. So we will search for an address in the direct physical map that we prefetch, and then we access our user space address, and we will observe a cache hit. And when we do that, we will actually find that this is a very straightforward attack. So it didn't take me much time to get this running. And I also talked to other people who reproduced this in a very short time. So you just iterate over the direct physical map, and it just drops you the direct physical map address that is maps to the same physical location. So this is great because this immediately leaks our address that we can exploit in a red to deer-like attack, and we don't need an additional information leak, we don't need the physical addresses, but if we know the base offset of the direct physical map, then we also have the physical address. And knowing the physical address, we can use that later on for other attacks. And as we already heard earlier, we have direct physical maps in different operating systems. So our attack works on Linux, on OS X, it works on Xen PVM. We tried that on Amazon EC2. That was fun. So you get sort of physical direct map addresses of the Xen hypervisor because the Xen hypervisor runs in ring 0. And then have fun with doing something with the physical address on Amazon. Our attack does not work on Windows because they don't have a direct physical map, but it's still fun to play with the other operating systems. So let's talk about using the physical address for other attacks. And as you have heard earlier in this talk, the cache, the level 3 cache, is physically indexed. So you need the physical address to actually compute where data is stored in the last level cache. And if you have this information, you can use this to build a powerful side channel. So we have seen side channels to infer user input like single keystrokes. Sometimes you can even narrow it down to the letter that has been entered. We have seen crypto key recovery in like one encryption, the 97% of the key bits recovered. We have seen cross VM attacks, cross core attacks, even cross CPU attacks this year. We have seen attacks on any architecture, so most attacks were on Intel architectures, but there is a Usenix paper by us at Usenix this year, and there we show that it works on ARM-based mobile devices. That's also fun. But for these attacks, it really helps if you know the physical address, because there is a mapping from physical addresses to the cache slices, the last level cache slices. And this function has been reverse engineered, so we can use the function if we have the physical address, but usually we wouldn't have the physical address in the first place. Another attack that can benefit from knowing the physical address is rowhammer. So if you know the physical addresses for a rowhammer attack, you can actually craft a much more efficient attack. For those of you who don't know rowhammer, it is basically a bug in hardware where you access memory locations in a high frequency, and at a different random memory location that you probably cannot access, a bit flips, and you can exploit that. It has been shown by Sebon and Dulian, who have presented this last year at Black Hat. You can gain root privileges with that. So rowhammer is pretty much like slamming a door repeatedly to break into a neighbor apartment. That is how Motherboard Vice described it when we presented rowhammer in JavaScript last year. So it works pretty much like this. So you activate one row, and then you activate another row, and they are always copied to the row buffer. And if you do that in a high frequency and often enough, you will see bit flips in the row between those two rows that you actually access. Now, to actually do this, you need to know which memory locations, which physical addresses map to these two rows. And therefore, we need to know how the DRAM is organized. And if you look at a modern system, you probably will have multiple channels that are the modules that you have in your system. And each of those modules will probably have multiple sites that are the ranks of the DRAM module. And then each chip is further divided into banks. So you have up to 8 banks. You have definitely 8 banks on DDR3, and you have up to 16 banks in DDR4. And these banks are further divided into the rows that you actually want to access. So you need to know the mapping from physical addresses to channel, to rank, to bank, and then you can access memory locations in the same row. So why does actually the bit flip happen here? DRAM cells lose their charge over time. They leak the charge, and if you let them leak the charge long enough, they would lose the value that they stored. So you need to refresh the value that is stored in the cell very frequently. And this is done by just reading the value from the row and writing it back. If you don't do this fast enough, then you will have data errors, you will have bit flips. Now, it has been found with when researching the row hammer bug, it has been found that proximate accesses can increase the probability of a bit flip, and this is the reason for this is that the cells leak faster upon proximate accesses. We have reverse engineered the mappings from physical addresses to memory, to the actual channel rank and bank. And this is also a Usenix paper this year. And we need the physical addresses then to compute where we want to hammer. OK.
So just to summarize, with a direct physical map, we're able to defeat SMAP and SMEP. And we're able to leak physical addresses. And with these physical addresses, we're able to perform other attacks, specifically cache attacks and row hammer attacks. This leads us to our final slide. And what we got here is, what we hope to bring across here is that CPU design is security relevant. In specific, that prefetch leaks significant information. The information that we get here, we can use to locate a driver in the kernel and thus break KASLR. But that's not the only thing that we do. We can break SMAP and SMEP, and we can get physical addresses to assist in other attacks. That was our talk, I think. Thank you.
I've got a question for you. So if I understand correctly, you need to be able to read your own processes page tables in order to know what addresses are safe to search for the kernel mapping without causing a page fault. Is that correct?
The prefetch instruction doesn't cause page faults, yeah.
But you said earlier that you can only search pages, I forget which of your...
You can only search for memory locations that are actually mapped, yeah. All pages that are not mapped yet, that would still require a page fault to occur, you find them as not mapped, so it's not valid.
So do you need to know your own page table mapping before you can start searching for those 1 terabyte chunks, or no?
Oh, no, no.
Okay. Thank you.
Any more questions? Thank you.